Hey there. Okay, so continuing on with Fermi-Dirac statistics. Hang on just a second. Sorry about that. So continuing on with Fermi-Dirac statistics, we discussed how the Dirac model of conduction, the semi-classical model, doesn't work. So of course it doesn't, because they're quantum particles. So we talked about how there are 3 different distribution functions. Here's a plot summarizing some of those distribution functions. And of course, we're going to go with the Fermi-Dirac distribution because the electrons, the conduction electrons, are half-integer spin. They're fermions. And so we're going to go with the Fermi-Dirac distribution. So this is the Fermi-Dirac distribution function summarized here. You have your normalization constant here on the bottom in the denominator, e to the e over kt, and then plus 1. Remember, T is the temperature, K is Boltzmann's constant, and E would be the energy of the conduction electrons. Now, we're going to talk about a quantity known as the Fermi energy. And the Fermi energy is the energy that the conduction electrons have. It's related to the average energy for the conduction electrons, as we'll see. And so, one way to think about the Fermi energy is to think about the value of the distribution function defined here at the Fermi energy. And it turns out that if you set the energy equal to the Fermi energy, then that sets the Fermi-Dirac distribution function equal to a value of 1/2 when you have a temperature T. Okay, so I'm going to show you what this normalization constant is if you set the energy equal to the Fermi energy and it has the value of 1/2 for the distribution function. So if you plug in the Fermi energy for E and you set the distribution function value equal to 1/2, then you have 1 over your normalization constant, e to the E Fermi over kt plus 1. Well, I can just flip both sides of that, take the inverse of both sides of the equation, and I can see that my normalization constant, e to the EF over kt plus 1 equals 2. And then, of course, subtract 1 from both sides. And then I can just solve for my normalization constant, and I get that my normalization constant is e to the minus E Fermi over kt. Okay, so that gives me the value of my normalization constant. And now I can stick that back into my distribution function. And there it is. There's my Fermi-Dirac normalized distribution function right there. The Fermi-Dirac distribution function is equal to 1 over e to the E minus E Fermi over kt plus 1. All right, so EF is our Fermi energy, and when E is equal to EF, then that sets the exponential term e to the 0, and that is equal to 1, which puts your whole distribution function equal to 1 over the 1 plus 1, which is 1/2. Now, let's think about what happens for the extreme temperature of the temperature going to absolute 0, okay? Now, in that limit, there's actually 2 possibilities. If the energy is greater than the Fermi energy, then the exponential term goes to e to the plus infinity, which is actually 1 over, then in the denominator you'd have infinity, and 1 over infinity is equal to 0. So that means that if your temperature is as it approaches 0, if your energy is greater than the Fermi energy, then basically that state doesn't exist, right? Because your distribution function cuts off at the Fermi energy. If your energy is less than the Fermi energy as T goes to 0, then that exponential term goes to negative infinity because E minus EF would be a negative number, and then you have e to the negative infinity. Well, e to the negative infinity goes to 0. So that means that you have 1 over 0 plus 1, which means that your distribution function goes to 1. Okay? So basically that tells you that your distribution function is 1 for the energies less than the Fermi energy, and it's 0 for the energies greater than the Fermi energy at absolute 0. Now, what does that mean? Okay, well, at T is equal to 0, all of your fermions are going to be in their lowest possible energy state. Okay? That's it. If you've got T equal to 0, your thermal energy is practically 0, and everything must be in its lowest possible energy state. Okay, so near temperature equals to 0, there's actually very little chance that thermal agitation is going to kick a fermion up to an energy greater than the Fermi energy, all right? Your energy distribution function is only going to get rounded out slightly Okay, so the probability that a fermion will have an energy greater than the Fermi energy is actually 0 at low temperatures. So what can you consider the Fermi energy as? Well, the Fermi energy, then, is the highest energy state available to fermions at low temperatures. So that sets the max possible energy that a conduction electron, say, can have as the metal goes to very, very low temperatures. Here's what the distribution function, the Fermi-Dirac distribution function, looks like for the temperature equal to 0, right? So here you have a value of 1 up to E Fermi, and then after that it's 0, okay? And then as the temperature goes to greater than 0, that step function just kind of gets rounded out, rounded off, and it looks like this, okay? It smears it out. Now, if you defined your Fermi temperature, just setting EF equal to KTF, then you have this. Now, if your temperature is much, much greater than the Fermi temperature, then the distribution function actually approaches just that simple decaying exponential, which is what you see for the Maxwell-Boltzmann distribution function. So for high temperatures, basically, you have a decaying exponential, and it doesn't look like a step function anymore, okay? So absolute 0, step function, temperature greater than 0 but still not too high, rounded out step function, and then high temperatures goes to a decaying exponential, and that's what your distribution function looks like for all the Fermi-Dirac statistics. Now, in a previous lecture, we already derived an expression for the density of states, and this was our gas of quantum particles, okay? So just to remind you, here's what that distribution function was. 2s plus 1 times 4 pi mc squared to the 3/2 power over hc cubed times the square root of 2e dE. That was our distribution function. Now if you get rid of your c's, okay, because we don't really need them for this particular case, and you set s is equal to 1/2, which it is for fermions, then 2s plus 1 becomes 2, and then you end up with 8 pi m to the 3/2 h cubed over h cubed root 2e dE. So that's our density of states. Now, to get the full numerical distribution function, you multiply the volume times the density of states times the Fermi-Dirac distribution function, and then you have it. So we're going to end up with N of E dE is equal to V, the volume, times 8 pi, the mass of the conduction electron to the 3/2 over Planck's constant cubed, times the square root of 2e, 1 over e to the minus EF over KT plus 1. And that is our Fermi-Dirac numerical distribution function, okay? Now, if you plot these things out, yet again, this is for t slightly greater than 0, and you have here your Fermi-Dirac distribution function. It's a step function. If you were to plot your density of states function, that's going to look like this. It's increasing as e to the 1/2 power. And then when you multiply those two things together, you get sort of the growth of the density of states at low energies, and then you sort of modulate that with the step-looking function that you have from the distribution function. And so you get a function that looks like this for your numerical distribution function. And you can see that it has a peak right there that's slightly below the Fermi energy. And so the Fermi energy is going to be related to the average energy of your conduction electrons by a relatively simple relationship that I'll show you in a few minutes. Okay, we can find our Fermi energy by setting t equals to 0 and normalizing that distribution function. Remember that if your temperature is 0, then that confines the energies of your conduction electrons to being less than the Fermi energy. And it also forces your Fermi-Dirac distribution function to equal 1, okay? So basically, you're sort of integrating your density of states more than anything else. But here's what you end up with. N is equal to, because that normalizes your distribution function, if you integrate N of E dE over all available states, then you should get the total number of particles, which is N. Okay, so here we have N equal to V 8 square root of 2 pi m to the 3/2 over h cubed. That's all the constant stuff. I pulled that outside of the integral. And then we're just integrating from 0 to the Fermi energy of the square root of E dE. Okay, now when you integrate e to the 1/2, which is the square root of E, then you get e to the 3/2, right, times 2/3. And then you're integrating from 0 to the Fermi energy, and so you just get 2/3 E Fermi to the 3/2 for your integrand, right? Now plugging that into the rest of the expression for the constants, we get our Fermi energy is h squared over 2n, 3n over 8 pi v to the 2/3. Okay, so it's a relatively simple expression to find the value of our Fermi energy, which you're going to do in homework. Now, keeping t equal to 0, you can see that the numerical distribution function is equal to your density of states for the energy less than the Fermi energy, and it's equal to 0 if your energy is greater than the Fermi energy. If you want to find what your average electronic energy is, remember to find an average, you just multiply the thing that you want the average of times the distribution function, and then you integrate that, okay? If you're integrating for temperatures below, for temperatures right at absolute 0, then it's only going to go up to the Fermi energy. So here we have 1 over n, integral from 0 to the Fermi energy, of the energy itself, what we're trying to find the average of, times our density of states, and we integrate that. If you perform that relatively simple integration, you can see that you get a value of 3/5 of your Fermi energy for your average or mean electron energy, okay? And then if you wanted to find it for the whole system, you would just multiply that times the number of particles in the system, n. So if you want the internal energy of a system of conduction electrons, it's 3/5 n times the Fermi energy, okay? So only those electrons that have an energy of about kT, within kT of the Fermi energy, will be able to absorb the thermal energy and jump to a higher state. Okay, so the fraction of electrons capable of participating in this process is on the order of the Fermi energy. All right, so what does this all mean? Because it might not be immediately clear. The Fermi energy is the energy that the conduction's electrons in the highest energy levels have at absolute 0, right? You can also say that this is related to their kinetic energy, because remember what's happening is these guys are zipping around in this lattice of ions, so they're zipping along. Okay, so you can relate that to their speed. For example, it's defined as the Fermi speed. So you just set the Fermi energy equal to 1/2 times the mass times the Fermi velocity squared. All right. Now, Fermi energies, if you look them up, are only on the order of a few eV. In your book, it works out the example for sodium, where the Fermi energy is 3.15 eV, which is about 5 × 10⁻19 joules. If you plug this into the equation for the Fermi speed that I just solved for you, you get 2 × 5 × 10⁻19 joules divided by the mass of an electron, 9.11 × 10⁻31 kilograms, and then you take the square root of all that. If you do that, you see that the Fermi speed is on the order of 10 to the 6 meters per second. What does that mean? That means that even at absolute 0, your electrons are traveling at incredibly high speeds. So, as opposed to the Maxwell-Boltzmann distribution function, which is a classical distribution function and shows that ideal gas molecules, which are zipping around at room temperature, would basically have their speeds go to 0 as the temperature goes to 0. Okay? This is a very different system. It's a quantum system, and thus the energies, the speeds, don't go to 0 at absolute 0, okay? There's going to be some residual energy even at absolute 0. So if you have that model in your head of molecular motion ceasing at absolute 0, well, it is kind of that way if it's a molecule zipping around, but it's maybe not that way if it's a quantum particle like an electron. Okay, then it's going to still have that residual energy and that residual speed left, even at absolute 0. All right, let me work an example for you where you find a Fermi energy. So let's take silver. Silver has, for example, 1 conduction electron per atom. It donates 1 electron to the C for every atom. And we're going to use the density of silver, which is 1.05 × 10 to the 4th kilograms per cubic meter, and the molar mass of silver, which we can read off the periodic table, 107.87 grams per mole. And then we're going to use that to find the density of conduction electrons in silver, then use that number to calculate the Fermi energy of silver and the Fermi speed of silver. So the solution to that is similar to what we did in the lecture on the Drude model. You have 1.05 times 10 to the fourth kilograms per meter cubed. You're going to change units on that density so that it's a number density of conduction electrons. So you've got to first convert from kilograms to grams, 1,000 grams in a kilogram, and then from grams to moles, 107.87 grams per mole, and so you're going to divide by that number, and then multiply by the number of atoms per mole. Avogadro's number, 6.022 times 10 to the 23rd. And then there's an understood 1 out here because for each atom, 1 conduction electron is contributed. When you multiply by all the numbers on the top, divide by everything on the bottom, you get 5.86 times 10 to the 28th conduction electrons per cubic meter. Now this is a number density, or N over V. Okay, it's the number of conduction electrons in per unit volume. So you set that equal to N over V and plug that into your equation for the Fermi energy. So what you do is you take that value, 5.86 times 10 to the 28th, multiply by 3 and divide by 8 pi, and then raise that to the 2/3 power. And then you multiply that times the constants out front. You've got h squared, which is Planck's constant, 6.626 times 10 to the minus 34 joules seconds. You square that and divide by 2 and the mass of an electron, 9.11 times 10 to the minus 31 kilograms. And then that gives you your Fermi energy, which ends up being 8.8 times 10 to the minus 19 joules. If you convert units into EV, that's about 5.5 electron volts. The conversion there is, of course, 1.602 times 10 to the minus 19 joules per eV. Now, if you plug that into your equation for the Fermi speed, 1/2 m Fermi speed squared equals the Fermi energy, then you can solve for your Fermi speed. Plugging all that back in, you get 1.4 times 10 to the 6th meters per second. So those are all those values for silver. All right? Now, we mentioned in the last lecture that the Drude model of conduction gives you a certain value for your conductivities, and that these values are off by an order of magnitude, okay? So it does turn out that when you use Fermi-Dirac statistics, you get good predictions in agreement with theory for what the values of the conductivity are. Drude, in his original calculations, thought that the mean free path of the electrons in the lattice was only a few tenths of a nanometer. But it turned out to be longer than his estimation by quite a lot. In fact, Einstein did some calculations. It's always Einstein, right? Einstein did some calculations in the mean free path, and he found that for copper, it should be on the order of 40 nanometers. Now, given that the spacing of atoms in a copper lattice is only maybe a few tenths of a nanometer, 40 nanometers is a nice long way for those conduction electrons to travel. If you plug that then into our formula for the conductivity would be the density N times E squared times the mean free path divided by the mass divided by the Fermi speed. Here we're plugging in the Fermi speed instead of the drift velocity because we've switched theories, and so we're going with the Fermi speed rather than the drift velocity. If you do that, you get a conductivity of 6 times 10 to the 7th inverse ohms per inverse meter. Now, the thing is, Drude originally thought that the electrons would actually scatter off the lattice sites of the ions, but that's a very classical way of thinking. He pictured these huge atoms sitting in this lattice and the electrons kind of binging into them like billiard balls would on a table. But in quantum mechanics, it doesn't quite happen that way, right? In quantum mechanics, you have a potential energy function, and then the electrons actually see this potential energy function. The potential energy function would be a regular array of these positive lattice sites, okay? So theoretically, a quantum particle, if the atom actually just sat there in its lattice site, a quantum particle would never scatter off the lattice site, and it would just move in sort of a sinusoidal way, magically dodging all of these lattice sites and never scattering off of them. And that would mean that theoretically, the electron would have an infinite mean free path and never scatter, okay, in a truly bulk solid that had no end. The reality, though, okay, is that these atoms don't just sit perfectly still within these lattice spots. They actually vibrate in their lattice spots and around them due to the temperature, okay? So they're sitting there wiggling back and forth in their lattice sites. So a quantum particle can't really predict exactly where that ion's going to be within its vibration during that amplitude of vibration. And so it will scatter off the ion because the ion is sitting there vibrating back and forth due to the temperature. And of course, the amplitude of vibration is going to increase as the temperature of the solid increases, which would mean that the conductivity is going to get lower and lower as the amplitude of vibration gets higher and higher, right? And that makes sense. Now, another thing that's going to happen is that the electrons are going to scatter off when there's a defect in the material. So, for example, you sort of picture this beautiful regular array of these ions sitting in this lattice, and you picture it as perfect. But that's not actually the way a real solid is. In reality, there's going to be vacancies in the lattice, and there's also going to be, say, instead of a copper ion, you're going to have a silver ion in there, and it might be a different size. So there'll be defects like that. Those are called substitutional impurities. Or you might have what are called interstitial impurities, where you have an extra copper atom stuck in where there's not really supposed to be a copper atom. The presence of those defects goes up as the temperature goes up as well. Okay, you get more defects within your lattice as your temperature increases. That's just something that you learn from materials science. So electrons scatter off the vibrational of the ions. It also scatters off defects. Both of these are temperature dependent effects, which is why in metals we see an increase in the resistivity, a decrease in the conductivity as the temperature goes up. Okay, so this is very consistent with a quantum model, and the Fermi-Dirac statistics quite accurately predict the conductivities and the heat capacities, which I'm not going to go into in these lectures, for electrons in the lattice. Okay, so hopefully that clears things up. Make sure to read the textbook and get back to me if you have any questions. Thanks.